Hello students, today I am going to start a new topic from the chapter Chemical Bonding and Molecular Structure, that is the concept of hybridization. Okay, in the formation of covalent molecules as a result of the overlap of atomic orbitals, we have seen that only the half-filled orbitals are involved in the bond formation. Okay, we know only the half-filled atomic orbitals take part in chemical bond formation. The number of such orbitals belonging to a particular atom taking part in the overlap or taking part in bond formation represents its covalency. Okay, the covalency. Okay, the number of half-filled orbitals, okay, belonging to a particular atom taking part in the overlap represents its covalency, the covalency of that atom. Okay, for example, please listen. We know in water, H2O, the central atom is oxygen. Its atomic number is 8. And its electronic configuration 1s2, 2s2, 2px2, 2py1, 2pz1. Okay, according to Hund's rule, you can fill the atomic orbitals in 2p orbitals according to Hund's rule. Yes, this electronic configuration indicates that the number of half-filled orbitals present in oxygen atom is 2, hence the covalency of oxygen is 2. Yes. Then the next example, in ammonia, the central atom is nitrogen, its atomic number is 7 and its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz1. Okay students, the number of half-filled atomic orbitals, present in nitrogen is 3, hence covalency of nitrogen is 3. Yes, in water the covalency of oxygen is 2, in ammonia the covalency of nitrogen atom is 3. Yes, that means what? The covalency is the number of half-filled atomic orbitals, okay, taking part in bond formation. That is the covalency of an atom. Yes. Okay, but the same principle cannot be applied to the formation of covalent compounds of elements like beryllium, boron and carbon. Okay, then please listen. Carbon, atomic number is 6. Its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. Okay. Yes, this is the ground state electronic configuration of carbon. Ground state electronic configuration of carbon. Ground state electronic configuration of carbon. Yes. Okay, this ground state electronic configuration indicates that the number of half-filled atomic orbitals present in carbon is 2, yes, 2px1, 2py1, hence the covalency of carbon must be 2. But, okay, in all its compounds, such as CCl4, carbon tetrachloride, methane, okay, ethane, etc. Okay, the carbon is tetravalent. Carbon is tetravalent. Actually carbon is not bivalent. Carbon is tetravalent. Okay, the valence of carbon is 4. Here in the case of CCl4, carbon forms 4 single bond with the chlorine. Here all the 4 valence electrons of carbon are used for the bond formation. Yes, then the covalency of carbon is 4. Carbon is tetravalent, not carbon is bivalent. Okay. Okay, that means in the case of carbon, the covalency is not equal to number of half-filled atomic orbitals present in carbon. Yes. In order to explain the tetravalency of carbon, it was proposed that all the time of chemical combination, one of its valence electron, one of the valence electron from this 2s orbital is promoted to the empty 2p orbital, the empty 2p Z orbital, the empty 2p Z orbital, which is in higher energy state. Okay, then that means to attain this tetravalency in the excited state, the one of the valence electron from completely filled 2s get promoted to the vacant 2p set. Then its electronic configuration becomes 1s2, 2s1, 2px1, 2py1, 2pz1. Yes, then the number of half-filled orbitals present in carbon atom, yes, becomes 4. Now the carbon atom attains tetravalency. We know these 2s and 2p orbitals, this half-filled 2s and the 3 half-filled 2p orbitals of carbon differ in their energies. If carbon make use of its 2s and all 2p orbitals as such for bonding, it will result in bonds of different strength and orientation. Okay, then that means what? If a carbon atom make use of these individual atomic orbitals for the purpose of, for the formation of bonds, yes, the bonds strength of bonds will be different. Yes, in CH form. Okay, the methane molecule CH4, this carbon forms bond with 4 hydrogen atoms. Okay, 4 hydrogen atoms. 1, 2, 3 and 4. 4 hydrogen atom. Okay. That means here the 4 CH bond is formed. One CH bond will be formed by the overlap of 2s orbital of carbon and 1s orbital of hydrogen. Okay, one CH bond is formed by the overlap of the 2s orbital of carbon, the half-filled 2s orbital of carbon and the half-filled 1s orbital of hydrogen. Then the other 3 CH bonds The other 3 CH bonds are formed by the overlap of 2p orbitals of carbon, 2p orbitals of carbon. Okay, 1s2, 2s1, 2px1, 2py1, 2pz1. Yes, and the 1s orbital of hydrogen. Okay. Okay, that means here now the individual, according to Weier's-Born theory, here the individual atomic orbitals take part in bond formation. Yes, these 2s orbitals and 2p orbitals of carbon. Okay, yes, having different energy and shape. Yes, actually our expectation is that yes, these 4 CH bonds, these 4 CH bonds have different bond length and different bond strength. Okay, the reason is that here individual atomic orbitals taking part in bond formation. These individual atomic orbitals of carbon, 2s and 3 2p orbitals have different energy and shape. Yes, okay. Then the bonds, the 4 CH bonds, these 4 CH bonds are not equivalent. That is our expectation. These 4 CH bonds of carbon are not equivalent. But the experimental studies show that all these 4 CH bonds, all the 4 CH bonds in methane, all the 4 CH bonds in methane are equivalent. That is, they are same in all respects. These 4 CH bonds having same bond length, these 4 CH bonds having same bond strength, etc. Okay, how it is possible? Why these 4 CH bonds are equivalent? Okay, this problem can be solved with the help of a concept known as hybridization. Okay, then what is meant by hybridization? Okay, first you read this definition for hybridization. Hybridization is the phenomenon of intermixing of atomic orbitals. Atomic orbitals are nothing but the electron clouds, okay, having different orientation. Yes, hybridization is the phenomenon of intermixing of atomic orbitals of slightly different energies and shape to get an equal number of new orbitals. These new orbitals are called hybrid orbitals of equivalent energies and shapes. And what is meant by hybridization? Hybridization is the phenomenon of intermixing of atomic orbitals of slightly different energies and shape to get an equal number of orbitals of equivalent energies and shape. Okay? So that means, yes, the atomic orbitals having different energy and shape undergo the process of intermixing. Okay? Or we can say the electron clouds having different energies and shape, okay, yes, undergo intermixing. Due to the or the process of hybridization, equal number of new orbitals called hybrid orbitals having equivalent energies and shapes are formed. The concept of hybridization was introduced by the famous scientist Linus Pauling. Okay, then what are the conditions for hybridization? The first condition, only the orbitals belonging to the same atom take part in hybridization. For example, yes, in the formation of a methane molecule, only the atomic orbitals belonging to carbon atom get hybridized, get intermixed. Only the electron clouds of carbon atom get hybridized. Yes. And second condition, the orbitals that participate in hybridization should have only very small energy difference. That means, here in the case of carbon, we know that 2s orbital and the 2p orbitals are involved in hybridization, and the energy difference, okay, yes, between these orbitals, okay, yes, is very, very small. That is the second condition. And the third condition, it is not necessary that only the half-filled orbitals take part in hybridization. Okay, in some cases, the completely filled atomic orbitals are involved in the process of hybridization. That means both half-filled and completely filled orbitals are involved in the process of intermixing or this hybridization. Okay, there are different types of hybridization: sp3, sp2, sp, sp3d, sp3d2, etc. We can explain the characteristics of hybridization on the basis of the sp3 hybridization. Okay, yes, on the basis of sp3 hybridization. Then what is meant by sp3 hybridization, or how sp3 hybrid orbitals are formed? Please listen. In this type, in sp3 hybridization, please listen. Here, the 1 and 2s orbital, this 2s, 1 2s. Then 1 2px, 1 2py, 1 is 2py, and 1 2pz orbitals of carbon get hybridized. In this type, 1s orbital and 3 orbitals of this atom, this carbon atom, okay, get hybridized to form 4 new type of equivalent hybrid orbitals. 4 new type of orbitals. The new type of orbitals are called hybrid orbitals. Okay? Yes. Please listen. 2s plus 2px plus 2py plus 2pz. Here forms the 4 hybrid orbitals. Okay? The 1 hybrid orbital. Okay? Yes, we can write here. Yes. We can indicate one hybrid orbital using one big lobe and a small lobe. This is one hybrid orbital, means one electron, new type of electron cloud. Okay, then second one. The third one. Okay, the fourth one. Yes. Okay, the fourth one. Then here the new type of orbitals are formed. These orbitals are called hybrid orbitals. Okay, here sp3 hybridization takes place. sp3 hybridization takes place, and these 4 sp3 hybrid orbitals are directed towards the 4 corners of a tetrahedron. Okay, the hybrid orbitals are nothing but electron cloud. Here the 4 electron clouds, 4 atomic orbitals, 4 electron clouds or 4 atomic orbitals, okay, having different energy and shape, okay, get hybridized or intermixed, okay, then forms the four new type of orbital called hybrid orbital, or we can say here forms for new type of electron cloud. These electron cloud repel each other and directed towards the four corners of a tetrahedron by making an angle, the angle between two hybrid orbitals. Yes, this one, 109 degree, 28 minutes. Then, yes, on the basis of this sp3 hybridization, we can discuss the characteristics of hybridization. First characteristic, only the orbitals with small difference in energy take part in hybridization. Here, the 2s orbital and 3 2p orbitals present in the valence shell of carbon atom undergo the process of hybridization. Yes, the energy difference between these 2s and these 3 2p orbitals, okay, yes, is very small. Okay, that is the first characteristic. Only the orbitals with small difference in energy take part in hybridization. Then, the second point, please listen, very important. The number of hybrid orbitals formed is equal to the number of atomic orbitals get hybridized. Please read. The number of hybrid orbitals formed is equal to the number of atomic orbitals get hybridized. Please listen. Here, 1, 2, 3, 4. Okay, these 4 atomic orbitals of carbon get hybridized. The 4 atomic orbitals get hybridized. And yes, after the intermixing, after the process of hybridization, forms 4 sp3 hybrid orbitals. That means what? The number of hybrid orbitals formed is 4, 1, 2, 3, 4, and the number of atomic orbitals take part in hybridization is also 4. That is the second point. That means if 4 atomic orbitals are involved in hybridization, the number of hybrid orbitals formed is equal to 4. Then if only 2 atomic orbitals, means 1s and 2s and 2px, then the hybridization becomes sp. Okay, 2 atomic orbitals undergo hybridization, then the number of hybrid orbitals formed equal to 2. Then if 3 atomic orbitals, means what? 1 2s and 1 2px, 1 2px, 2py. Okay, 3 atomic orbitals, 1s and 2p orbitals, then the hybridization becomes sp2. That we will discuss later. Okay, anyway, yes, then the number of hybrid orbitals are formed is 3. Okay, that is the second postulate. The number of hybrid orbitals formed is equal to the number of atomic orbitals get hybridized. And the third characteristic, the hybrid orbitals are equivalent energies and identical shape. We know the atomic orbitals involved in hybridization. Okay, yes, hybridization differ in its energy and shape. Okay, that means the atomic orbitals with small difference in energy and shape take part in hybridization. But okay, after the intermixing, after the hybridization, we know the hybrid orbitals are formed. These hybrid orbitals have equivalent energies and identical shape. Okay, these shape of the 1 sp3, second sp3, third sp3, 4 sp3. The shape of these 4 sp3 hybrid orbitals. Okay, the shape of these 4 sp3 hybrid orbitals are identical, and the energy also equivalent. That is the third characteristic. The hybrid orbitals have equivalent energies and identical shape. And the fourth characteristic, both half-filled and completely filled orbitals can hybridize. Okay. Here, in the case of methane, only half-filled orbitals of carbon get hybridized, but in some molecules, the molecules like ammonia, water, the completely filled orbitals also take part in hybridization. Okay, the formation of water and ammonia on the basis of hybridization. Okay, we will discuss it in next class. Don't worry. Yes. Then the fifth characteristic, The hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. Okay, already we have learned the individual atomic orbitals cannot form stable bonds due to the energy difference. Okay, but the hybrid orbitals are more effective in forming stable bonds. Stable bonds. Okay, stable bonds. Then the last characteristic, the hybrid orbitals are directed in space in some preferred directions to have stable arrangement. Okay, already we know these hybrid orbitals are nothing but electron cloud. According to VSEPR theory, these electron cloud repel each other and try to stay as far apart as possible to acquire a state of minimum repulsion or maximum stability. Okay, then to acquire a stable geometry, a stable arrangement, these hybrid orbitals directed in space in some preferred direction. In the case of sp3, we know 4 sp3 hybrid orbitals are formed. Then to acquire a stable arrangement, these 4 sp3 hybrid orbitals directed towards the 4 corners of a tetrahedron and acquire tetrahedral shape. Okay, then just see one example for a sp3. The example is methane. Okay, in methane we know the carbon atom is the carbon atom is sp3 hybridized. Okay, the reason is that in methane carbon atom must be formed 4 sigma bond. Okay, 4 sigma bond with hydrogen. Okay, yes, in order to form the 4 sigma bond, the number of hybrid orbitals, half-filled hybrid orbitals present in carbon must be 4. Okay, carbon forms 4 CH sigma bond. For the purpose of forming this 4 CH sigma bond, the number of hybrid orbitals in carbon must be 4. Yes, we know in sp3 hybridization, the number of hybrid orbital is 4 sp3. Yes, okay, then there is no doubt. In methane, the central carbon atom is sp3 hybridized. Then these sp3 hybridized orbital of carbon overlap with 1s orbital of hydrogen. And here forms 4 CH sigma bond. Yes, please listen. Here the overlapping takes place along the internuclear axis. We know if the overlapping takes place along the like this axial overlap, the bond formed is should be sigma. Here 4 CH, the carbon atom, the hybridization sp3. These 4 sp3 hybrid orbital overlap axially with 1s orbital of hydrogen, and here forms 4 CH sigma bond, and due to sp3 hybridization, the shape of methane is tetrahedral. Okay, students, in my next video we will discuss the different examples for this sp3 hybridization. Sp3 hybridization. Anyway, today we have learned the concept of hybridization, the conditions for hybridization, then the definition for hybridization, the characteristics of hybridization, then just we study the sp3 hybridization. We will discuss the sp3 hybridization in detail in my next class. Okay, students, goodbye, study well.